Okay, welcome back. This video is going to be a little bit of a quickie. Previously in the series, we got memory from the computer to the graphics card by mapping to a region in RAM, writing to that region, and then the graphics card read from that region. That's fine. However, there are different types of memory on the graphics card, and some of it can be mapped to. And it turns out the more high-performance memory can't be directly mapped to from RAM. It's just it's not so good. It needs to be closer to the metal, as it were. So that's what we'll be doing today. We'll be creating a regular buffer and sending data there from RAM, and then we'll be scheduling a job on our graphics queue to transfer internally within the graphics card. So how do we do this? Well, how do you eat an elephant? One bite at a time. We'll head over to memory, and what I want to do is if we go down to, where are we? Find memory type index, no, down below there. Here we are. Okay, in allocate memory buffer, here we are hard coding the memory usage, or the memory properties that we want to request. I'm going to change that. So we'll go up here to the buffer input and we'll specify the memory properties that we want to request as one of the fields. And then down below, I'll just minimize a lot of this. Down below, we can request that. So we can go okay, so this is making the function more general, so we can create pretty much a number of different types of buffers. So now we can go to the Vertex menagerie and look at the finalize section, and I'm going to refactor this so that we are creating a, we'll call it a staging buffer. Okay, good. So we have the same properties that we hard-coded before, and I'm also going to change the usage to a transfer source, because the only purpose here, after we map the data to it, the only purpose is to transfer from it to our other buffer. So I'm going to grab this vertex buffer and I'm actually going to move that down underneath. And right now I'm going to create a staging buffer. This staging buffer is a completely temporary object, so we can grab the deletion functions and perform those at the end of the work, at the end of the function. And also, here after we create the staging buffer, we send memory to it from the CPU. So I'll just modify this so that we are dealing with basically sending it to the staging buffer. So again, as a revision, we map to the staging buffer's memory location, and then we move the lump, the data in the lump, to there, and then we unmap the staging buffer's memory location. Okay, so after we've done that, we then want to create a vertex buffer, and in order to do that, all the fields in this input chunk are pretty good. I'm just going to re-specify two things. I'm going to specify the usage. We are going to now use this as a vertex buffer. Come on, come on. And what is it? As well as a vertex buffer, it will be a transfer destination. And then in the memory properties, we just need to specify that this will be device local. Device local is the flag, the code word for that high performance memory that we want to get to. Okay, so at this point we have our staging buffer, our temporary buffer, and it's full of the data that we want to use. And we've just created the vertex buffer. So we need a general function which will copy from one buffer to the other. So we can go to memory and create that function. So yeah, work in progress. Let me just quickly explain what this is. Source buffer and destination buffer. In a copy operation, that should make sense, as should size. We need to include a queue because this is a job. This isn't a one-time thing. We have to submit the work, prepare it, submit it, you know. And the graphics queue will work just fine here, but we do need a queue to submit that work on. And the command buffer is necessary because it's a job, which means we need to record the list of operations, a list of commands before submitting that. So let's go ahead and code this up. Okay, so just a whole lot of typing. Most of it should be self-explanatory. So this command buffer is the main command buffer, which is being reused, so it's a good idea to reset it. What's going on here? Not defined? Oh, that must be a capital V. I'll get to that in a second. Okay, so where was I? It's a good idea to reset the command buffer. And yeah, we set up, so we begin the command buffer anew, and then we specify the region that we're copying. Should be pretty straightforward, just offsets and size, and then we issue the command to copy that region, and then we submit that work. Yeah, we submit that work and just send that off. Now we have a fence, because if we're doing a more complicated operation, we might want to synchronize it more explicitly rather than just waiting for the queue to idle out. So remember, a fence is because this function will do its thing pretty quickly, but the underlying work may still be ongoing, and we could signal a fence when that underlying work is complete, so that if we have a bunch of these submissions running at the same time, they are not running into each other. But no, this is good. I'm happy with this. But we can see, where am I? We can see that we're now grabbing a whole bunch of new things like queue and command buffer. So what we'll have to do is go back to the Vertex menagerie and define a new class, which I'm going to call Finalization Chunk, which will hold the information which is used to minimize that, hold the information which is used to finalize the vertex chunk. Okay, it's looking good. So then we can go down to the finalize function and give this a different argument. So we can give it a finalization chunk. Okay, great. Now it's gonna, this is gonna complain, so we can just fill these in. Or rather, it would complain if my computer wasn't being slow, but yeah, okay, I think that's fine. Alright, cool. So, we've got all of this set up. All we need to do is copy that buffer over. So we'll go okay, so that's all looking good. I swear this is the final step. We just need to go to the engine, and where we create the assets, we need to pass in the appropriate fields to the, where are we? To the finalization chunk. Okay, so all of this, all of this, all of this. Now we'll just set this up. Okay, so it's a lot of typing, but we've got that there. We can then pass that in as an argument, and fingers crossed this should be working. So we'll just head over to main, give this a shot, and there we have it. So performance difference may not be extremely dramatic. After all, the bottleneck is the CPU performance and the fact that it's Python. That's it. That's the cost of code, basically. But we do have the moral superiority that we're using the most optimal memory type. For whatever that counts as. And this is a skill that which we'll be using later on to get other resources such as images into the optimal memory type. Anyway, hope you enjoyed that. Hope you learned some stuff, and I will see you again soon. Bye.